In this lecture, I am going to explain you diamond structure. Diamond structure is FCC diatomic. It is FCC diatomic. In the last lecture, we studied NaCl diatomic structure, which is also FCC diatomic. But in NaCl FCC diatomic structure, there are two different basis atoms. One belongs to chlorine and other belongs to sodium. But in case of the diamond, which is FCC diatomic, and it is having both the basis atoms as carbon atoms. In this case, both, both basis atoms are carbon atoms. And as you know that carbon atom has 4 valence electrons. And these 4 valence electrons are shared with 4 nearest carbon atoms. These 4 valence electrons are shared with 4 nearest carbon atoms, and it forms a tetrahedral structure. It forms a tetrahedral structure in which there is a covalent bond. Okay, there is covalent bond between the carbon atoms. This covalent bond is very strong. The covalent bond is very strong because in this case electrons are tightly bound between atoms, between carbon atoms. And so the covalent bond is very strong. Reason of that is because of that diamond is hardest material. Diamond is hardest known material. If the scale of hardness is 1 to 10, then diamond has 10 points. Hardness is the maximum, that is 10. Diamond is also known for its durability. And it has a high index of reflection and refraction. Reflection as well as refraction. Now, as I said that in diamond unit cell, both the basis atoms are carbon atoms. But it, this carbon atom in diamond exists in two crystal forms. In diamond, carbon atoms exist in two forms. One of the form is cubic and another one is hexagonal. So there are two crystal systems possible for the diamond. So diamond exists in cubic forms as well as in hexagonal form. Out of these two crystal systems, cubic is very common. It's a commonly observed, and hence we are going to study only cubic crystal systems. Now to describe the diamond structure, let us describe it as there are two interpenetrating FCC monoatomic sublattices. You can say that diamond lattice is formed. Okay, this is one way of description. It can be described as diamond lattice is formed by two interpenetrating FCC monoatomic naturally sublattices of carbon atoms. Carbon atoms. So in the diamond lattice, or you can say that initially there are two FCC sublattices of carbon atoms. Then they are interpenetrating into each other and form a single lattice, and that is the diamond lattice. But how these sublattices are interpenetrating? They are interpenetrating such that if origin of one sublattice is at 0, 0, 0, then origin of other sublattice is at a by 4, a by 4, a by 4. So you can see here the difference between NaCl type and diamond type. NaCl is also FCC diatomic, diamond is also FCC diatomic. But in NaCl, there are two basis atoms, one is sodium, another one is chlorine. And the orientation of that basis is if one sublattice is at 0, 0, 0, then other sublattice is at a by 2, 0, 0, 0. But in case of carbon, in case of a carbon atoms in diamond, there are two sublattices. Both the sublattices is of carbon atoms, and these two sublattices are interpenetrating into each other such that if origin of one carbon sublattice is at 0, 0, 0, then origin of another carbon lattice is at a by 4, a by 4, a by 4. Now, for these two sublattices of carbon atoms, I am showing unit cells. So let me show first unit cell for one sublattice of the carbon atom. It is cubic. And this is FCC monoatomic sublattice. So in this FCC monoatomic sublattice, there are 8 carbon atoms at the 8 corners, and there are 6 face center atoms. This is front surface, this is backside surface. So this is one sublattice. We need cell in one of the carbon sublattice. Similarly, let me show you the unit cell in another sublattice. This is also FCC monoatomic sublattice. Sublattices are monoatomic. There are, in this case also, there are 8 corner atoms and 6 face center atom, front surface, backside surface. Now these two FCC sublattices of carbon atom are interpenetrating into each other. How they are interpenetrating? They are interpenetrating such that if origin of this atom or this sublattice is at 0, 0, 0, then origin of this one is at A by 4, A by 4, A by 4. So after interpenetration, this atom comes and sit at this position. This position is A by 4, A by 4, A by 4. Because of this kind of interpenetration, only 4 atoms of this second unit cell comes inside the unit cell, inside this unit cell. Other goes out of the unit cell. And that form a unit cell of carbon, unit cell of diamond. Let me draw a unit cell of diamond. Drawing of the unit cell is very important. It carries mark. Okay, this is the cube. And in diamond, in this first unit cell, as you can see here, there are 8 corner and 6 face center carbon atoms. Let me show that. There are 8 corners. These are the 4 of upper surface, of bottom surface, and then there are 6 face center. These are the 4, and this one is of the front surface, and this is of backside surface. So these are the 8 corner atoms and 6 face center atoms. Now 4 atoms of this unit cell comes inside the unit cell, this unit cell. So This atom is at the position A by 4. I am showing this color filled to just identify which are the inside atoms and which are the FCC atoms. So the four atoms of this unit cells comes inside the unit cell in this unit cell such that there is a one atom along each body diagonal. In this case, we can draw four body diagonals. So there are four atoms, each one along one body diagonal. So this is the one. Another one is this. Now this atom, the first atom is this one, and this is along the body diagonal when we connect this atom with this atom. Along their body diagonal, this atom is. Then this atom, that atom is along the body diagonal drawn from this atom to this atom. Then there is atom over here, and that carbon atom is along the body diagonal drawn from this atom, which is backside atom with this front side atom. And the fourth one is over here. This is the fourth one. And this is at body diagonal drawn from this atom to this atom. So this is the unit cell of diamond. As you can see there are 8 carbon corner atoms, 6 carbon face center atoms, and 4 carbon atoms are inside the unit cell. I will slightly modify the position of this. Not exactly looks like. Let us put that over here. So these are the atoms in diamond. Now, as I told you that each carbon atom forms 4 covalent bonds. It's not possible to show all the covalent bonds of all atoms, but here I am going to show the covalent bonds of inside atoms. So, if you consider this, this atom is very close to the front surface because it is at a distance a by 4. So that atom forms one covalent bond with its nearest, that is one corner atom, and 6 and 3 nearest face center atoms. And with this atom, this one is face center of the front surface. And as I told you that this atom is close to the front surface. So it forms with this covalent bond with this face center atoms. Then let's consider the another one. This one. This one is close to the backside surface. So it forms one covalent bond with the corner. Always remember that these inside atoms in the unit cells form one covalent bond with the nearest corner atom and 3 covalent bonds with nearest face center atoms. So this atom is close to the backside surface. So one covalent bond with the corner, then this would be the nearest one. This is nearest one. And this is close to the backside surface, so it forms fourth covalent bond with the face center atoms of backside surface, not with this, with this. Then let us consider this atom over here. This is along the body diagonal drawn from this atom to this atom. So it is obvious that this atom is close to the front surface. Okay, that one is close to the front surface. So it forms one covalent bond with the corner, one covalent bond with this corner, nearest corner, one with this face center atom, one with this face center atom. And as I said, this is close to front surface. There is one atom over here. This is the face center of the front surface. This is a face center of the backside surface. And this atom is close to the front surface. So it forms a covalent bond with the front face center atom with this. Then consider this atom. This atom is on the body diagonal drawn from this atom to this atom. This is backside atom. So this atom here is close to back surface. So it forms a covalent bond with the nearest corner. Nearest corner atom is this. So one covalent bond with this. Nearest face center, this and this. And the fourth nearest face center is the face center of backside surface, because I said this atom is close to backside surface. So the fourth covalent bond it will form with the face center of backside surface. And this is the unit cell of diamond. Okay, in the diamond unit cell, as you can see, there are 8 atoms at the 8 corners, 6 face center atoms, and 4 atoms are inside the unit cell. Let us characterize this unit cell now. Let us characterize unit cell of diamond. So unit cell, as we know that this is FCC diatomic. Atomic basis, 2 carbon atoms per lattice point. Then orientation of atomic basis. Orientation of atomic basis. If one carbon atom is at 0, 0, 0, then other is at A by 4, A by 4, A by 4. No need to mention vice versa because both are the carbon atoms. So that is the orientation of atomic basis. Then let's find effective atoms per unit cell. Effective number of atoms per unit cell. As I told you, there are 8 corner carbon atoms. Contribution of each corner atom is 1 by 8. So 8 into 1 by 8 is the contribution of corner atoms, plus there are 6 face center atoms. Contribution of each face center is half. Plus there are 4 atoms which are inside the unit cell. That inside atoms are not shared with any other unit cell. and so the total is 8. Effective number of atoms is equals to 8. Then coordination number. It is a tetrahedral structure. Each carbon atom forms 4 covalent bonds with its nearing 4 carbon atoms. So coordination number is 4. Now where these atoms would be in contact with each other. The origin of this is 0, 0, 0, and origin of this one is at A by 4, A by 4, A by 4. These two atoms are basis atoms. This and this are the basis atoms, and basis atoms are in contact with each other. So let us find lattice constant in terms of atomic radius or atomic radius in terms of lattice constant. To show that, I have to draw one more diagram. As I told you, the basis atoms are in contact with each other. This is our corner atom, and basis atom of this corner atom is over here. Let us say it is over here. So these two atoms are in contact with each other. As I said, coordinate of this one is 0, 0, 0. Coordinate of this is at A by 4, A by 4, A by 4. And what we have to find is distance between them. This distance we have to find where these two atoms are in contact with each other. To find that distance, let me show you first XY plane here. This is y-axis and this is the x-axis. So this is XY plane in which, let us say, this point is A, this is B, this is C, and this one is D. So A, B, C, and let's say this is E. So this A, B, C, E is XY plane. In this XY plane, AB equals to BC, and that is equals to A by 4. That is X coordinate and Y coordinate. Now I want to find this AC. I am drawing the line here, AC. This angle over here is 90 degree. Therefore, AC we have to find. And you know that this AC square is equals to AB square plus BC square. AB, BC both are A by 4. So this is A square by 16 plus A square by 16. That is 2A square by 16, which is nothing but A square by 8, which is AC square. And that's why AC is equals to A upon 2 root 2. Now this, let us consider another triangle. C, I'm joining C with the center here. That point is D. And as you can see in this triangle, that is ACD, angle C is 90 degree. This is right angle triangle. Here DC is the height. along the z direction. So that DC is equals to a by 4, z coordinate. And we know what is AC. And what we have to find is AD. So in this case, AD square is equals to AC square plus CD square or DC square. AC square is A square by 8 plus CD square, CD is A by 4, so it is A square by 16, or that is equals to 3A square by 16, which is AD square, and so AD is root 3A upon 4. So the distance between these two atoms, two basis atoms, is root 3A by 4. In this case, root 3A is body diagonal of the cube, and root 3A by 4 is a quarter of the body diagonal. So along the quarter of the body diagonal, two basis atoms are in touch with each other. So this root 3A by 4 is equals to 2R. 1R of this plus 1R of this. Root 3A by 4 is 2R, or you can write A is equals to 8R by root 3, that is constant, or R is equals to root 3A by 8, which is atomic radius. Then let's find packing fraction. Packing fraction. Packing fraction is ratio of volume of effective atoms in the unit cell to volume of the unit cell. In case of diamond, there are 8 effective atoms per unit cell. So in this case, it is volume of 8 carbon atoms divided by volume of unit cell. All atoms are carbon atoms. So volume of 8 carbon atoms is 8 into 4 by 3 pi r cube divided by volume of the unit cell, which is a cube, but a is this. So it is 8r upon root 3. This is a, and volume is cube of a. Then after simplification, we get 0.34, that is packing fraction. So 0.34 is a fraction of the volume occupied by carbon atoms in the unit cell, rest is wide, or its packing efficiency, which is packing factor into 100, that is 34%. So only 34% of the volume is occupied by carbon atoms in diamond unit cell, and the rest is wide.